Hello students and welcome to the lecture. So students, as we know that we had started the discussion over the modern physics, right? And so far we have done with the two parts, part 1 and part 2. This is going to be our modern physics part 3. I hope that you have revised the previous two parts in the well enough manner before you have come for this lecture, because that is for your own benefit. So let's see what we are going to discuss in this particular lecture. In this lecture, we will talk about the three types of radiations: alpha, beta, and gamma decay, alpha decay, beta decay, gamma decay, artificial and induced radioactivity, nuclear reaction, nuclear energy, energy from the nucleus, and the nuclear fission. Okay. Three types of radiations: alpha, beta, and gamma decay. Alpha decay, beta decay, gamma decay, artificial induced radioactivity, nuclear reaction, nuclear energy, energy from the nucleus, and nuclear fission. This is what we are going to discuss in this particular lecture. Okay. So here you can say that last two lectures we had talked about the radioactivity. Okay, like in the part 1 we had discussed about the radioactivity. In the part 2 we had discussed about the alpha, beta, and gamma rays. In this part 3 we are going to take it further and we will discuss it as a type of reaction, as a type of decay, how we could introduce the artificial and induced radioactivity, nuclear reaction, what do we mean by it, what is the nuclear energy that is released from the nucleus of an atom, and then the nuclear fission. Okay, so that's why this is what I'm again telling you. If you are not revising the lectures, you won't be able to connect the dot properly, because the dots are interconnected to each other in every part. Okay. Before starting this lecture, as usual, we have the small disclaimer over here that we are required to understand before we proceed further. Disclaimer goes like: the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this tag and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Now, let's begin with the alpha, beta, and gamma decay. So, the radioactive nuclei are unstable and emit radiations to achieve the stages of greater stability. Like we know, radioactive phenomenon we observed in the elements where they having some kind of instability. Okay, so when the element is actually unstable, it starts decaying the alpha, beta, and gamma, or you can say when the nucleus is unstable. Okay, then what happens? Through this emission or through this radiation, actually it reduces the instability and gathers the stability. Okay, that's why what we say as the achieves a greater state of stability. The emission of any of the alpha, beta, and gamma radiation and changes the original nucleus called the parent nucleus into two new nucleus that we call as the daughter nucleus. Okay, so we could say when the emission is actually going on for the alpha, beta, and gamma radiations, the original nucleus that we often regard as the parent nucleus, that nucleus got converted into the two new nucleus that we call the daughter cells. Okay, sorry, not two. Into the new nucleus that is stable, and that what we call as a daughter nucleus. The daughter nucleus may be radioactive and disintegrate further to form a still new nucleus. The process continues till a stable nucleus of lead 2 equals 282 is formed. So we could say when the radioactive nuclei start emitting the radiation in order to achieve the state of stability, actually the parent nucleus, the original form of nucleus, that got converted into the daughter nucleus. This daughter nucleus will further disintegrate and radioactivity will be there until or unless it reaches the nucleus of lead which is stable, which is 2 is equal to 82. Okay, so till then this decaying process, disintegration, and radioactivity will continue. Then Rutherford and Soddy suggested the following rules governing the radioactive decay. First is the algebraic sum of charges, atomic numbers before and after disintegration must be the same. First rule, the sum of mass numbers before and after disintegration must also be the same. So we could say the atomic numbers and the atomic mass, these must be same before and after the disintegration. So these two laws told by whom? Rutherford and Soddy. They were the one who gave these two laws. The algebraic sum of charges, the atomic numbers before and after disintegration must be the same. And the sum of mass numbers before and after the disintegration must also be the same. Got it? Now let's have a discussion over the alpha decay. So when a nucleus emits an alpha particle, its mass number decreases by 4 and charge number decreases by 2. Okay, this is the first thing. In general, alpha decay is represented as Zxa equals to Z minus 2Xa minus 4 plus 2He4 plus Q. Here, Q is the energy release in the decay. So we know whenever the decay happens, there must be the radioactive energy which is going to be released. So here we use the Q to represent this. Okay. Now the beta decay. It is the phenomenon of emission of an electron from a radioactive nucleus. So when the radioactive nucleus actually emits the electron, then what we call as a beta decay. Or technically we could say beta decay is actually the phenomenon of emission of an electron from a radioactive nucleus. When a parent nucleus emits a beta particle, therefore an electron, the mass number remains the same because the mass of electron is negligible in that case, and atomic number actually increased by 1. In general, we could write it as Xa equals to Z1Ya plus minus 1 E0 plus Q, where Q is the energy released of beta decay, similar like the alpha decay. Now, gamma decay. So it is the phenomenon of emission of gamma ray photon from a radioactive nucleus. So when the gamma ray photon actually got released cause of the emission of radioactive nucleus, that is what we call as the gamma ray or gamma decay. This occurs when an excited nucleus makes a transition to a state of lower energy. As nuclear transition to a state of lower energy, and nuclear states have energies of order of MeV, therefore the photons emitted by nuclei have very large energies or MeV and hence much smaller wavelength of 0.01 angstrom. Such short wavelength electromagnetic waves emitted by the excited nuclei that we call as the gamma rays. Okay, so remember, gamma rays are actually the short wavelength electromagnetic waves that got emitted by the excited nuclear, or you can say the unstable nuclear that got into the state of exciting. Since photons do not have any charge or rest mass, therefore in gamma decay, daughter nucleus having the same charge number and the same mass number as those of parent nucleus. The gamma decay could be represented as Zxa equals to Zxa plus gamma. Okay, so this representation we use to denote the gamma decay. After an alpha decay or beta decay, the daughter nucleus is usually an excited state and achieves stability by the emission of one or more gamma ray photons. For example, Beta decay of 27CO60 transform it into an excited 20A Ni60 nucleus. This reaches the ground state by emission of gamma rays of energy of 1.17 MeV and 1.33 MeV. By studying the energies of gamma rays that are actually emitted, we could obtain the energy levels of nucleus. Now, let's have a discussion over the artificial and induced radioactivity. So, in a natural radioactivity, the nuclei disintegrate on their own without any external provocation. So, we could say, suppose if you are having a unstable nuclei. So, this unstable nuclei will start emitting by itself or disintegration by itself. We do not require to provocate anything on external basis. Later on, it was discovered that certain elements which are otherwise stable could be made to disintegrate by bombarding them with suitable acidic particles. So here we are saying that naturally we don't have to do anything to disintegrate the excited nuclei. That will already. Okay. But when we want to artificially induce the formula of radioactivity, we could do it with some elements that are actually stable. Naturally, these elements are stable. We have to do some external provocation in order to make them able to disintegrate the rays. And how we could do them? We could bombard them with suitable acidic particles. Okay, for example, this is the stable element or nuclei. Here we have bombarded certain particles on it or suitable particles on it that got excited and now it is emitting the rays. Okay, so that's how artificially we introduce the radioactivity in the stable elements also. This phenomena of disintegration of otherwise stable nuclei by bombarding them with suitable projectile is what we call the artificial radioactivity. Usually, the disintegration stops as soon as the bombardment is over. So remember, because it is what we are doing artificially, it is not naturally. Okay, so the disintegration will only continue up to the bombardment continues. When the bombardment stops, the disintegration will also stop because the nuclei is stable. We are making it to become unstable by bombarding the suitable particles. Okay. And this is the standard definition of artificial radioactivity. Phenomenon of disintegration of otherwise stable nuclei by bombarding them with the suitable projectiles is what we call artificial radioactivity. We could not use any projectile for this purpose. We required the suitable projectile. However, if the bombarded element keep on disintegrated, even after the bombardment stop, the phenomenon is called induced radioactivity. So now here you are seeing the two terms, artificial and induced radioactivity. Okay. So the one thing that you are required to make clear in your mind is that we are talking both of them in the same manner of stable nuclei. Okay. Like we could say element with stable nuclei, or you can say some elements with stable nuclei could be converted into the excited state by bombarding them with suitable particles. Okay. So we could say there are the two conditions, first condition and the second condition. In the first condition, we bombard the element with suitable particles and then it start emission of alpha rays, beta rays and gamma rays. Okay. So this is what we call the artificial radioactivity. Okay. But what was the condition in the previous slide? That this bombardment continues this disintegration continues till the bombardment continues. Once the bombardment stops, this disintegration will also stop. Okay. So this is the case for artificial radioactivity. But when the bombardment stops, but still there is a disintegration, then that is what we call as the induced radioactivity. So remember, for artificial radioactivity, we could say to make the stable nuclei into the unstable nuclei by bombarding the suitable particles on the element, that is what we call as the artificial radioactivity. If the bombardment stop but still the emission continues or disintegration continues, that is what we call as the induced radioactivity. Okay. Thereafter, Curie and Joliot, they observed that boron, when bombarded by alpha particle, continued to disintegrate further even after the bombardment stopped. So, boron having the capacity to induce the radioactivity, and that is observed by whom? That is observed by Curie and Joliot. Okay, so in their laboratory they had observed, then when they bombarded the alpha particle on boron and then they stopped it, but still the disintegration continues in boron, to showing the phenomenon of induced radioactivity. It could be represented as 5B10 plus 2He4 equals to 7 and 14 equals to 7 and 13 plus 0 and 1. Thereafter, second case, and 7 and 13 equals to 6C13 plus 1E0. The half-life of 7 and 13 is 11 minutes and it is converted into 6C13, emitting a positron. Now, after finishing this, let's have a look over the nuclear reaction. Okay, so in general, you have seen the nuclear power plants. Okay, on TV, you can say maybe you have one in your area. Okay, so in the nuclear power plant, we use the nuclear reaction to produce the energy that could be converted into the electricity or the power generation later. All right, so how we produce the nuclear energy and how it is also, you can say, regarded as a weapon. Nuclear bombs you have heard about. Okay, so this nuclear reaction could be converted into the nuclear bombs and nuclear energy both. So now it is important to learn about it. So a nuclear reaction represents the transformation of one stable nucleus into another nucleus by bombarding the former with suitable high energy particles. So we having one stable nucleus, we transferred it to another when we bombard a suitable energy particles on it. That is what we regard as the nuclear reaction. Symbolically, we could represent a nuclear reaction as ZXA plus 2He4 equals to Z plus 2. Ca plus 4 equals to Z plus 1. Ya plus 3 plus 1H1 plus Q. Okay, so this is what we use to represent the nuclear reaction. Here, X is the target nucleus bombarded by an alpha particle, that is what we call projectile. C is the compound nucleus which is unstable. It disintegrates to give a product nucleus Y and a product particle proton. The reaction is named alpha P reaction after the name of the projectile alpha and the product particle P. In the nuclear reaction, Q is the total energy change in the reaction. It is what we call nuclear reaction energy or Q value of the reaction. In all types of nuclear reaction, the following observation laws are obeyed. First is conservation of linear momentum. Second is conservation of total energy. Third is conservation of charge. Fourth is conservation of number of nucleus. Okay. So these laws observed during the nuclear reactions: conservation of linear momentum, first law; conservation of total energy, second law; conservation of charge, third law; conservation of number of nucleus, fourth law. Rutherford was the first to perform an experiment in an artificial transmutation of elements. He discovered the nuclear reaction as 7N14 plus 2He4 equals to 9F18 equals to 8O17 plus 1H1. Now, nuclear energy is the energy from the nucleus. The nuclear reaction involving nuclei with A is greater than 170 constitute the nuclear fission, and the nuclear reactions involving the nuclei with A which is lower than the 30 constitute the nuclear fission. So remember, for nuclear fission, we required a nuclei which is A greater than 170. For nuclear fission, we required a nuclei with A is lower than 30. Okay, so there are the two types of nuclear reactions. First is nuclear fission. Second is nuclear fission. Fusion and fission. Okay, nuclear fusion and nuclear fission. Thus, two distinct ways of obtaining energy from nucleus are: first is nuclear fission. Second one is nuclear fusion that just I have showed you. For the nuclear fission, the nuclear fission is actually the phenomenon of splitting of a heavy nucleus, usually when A is greater than 230, into two or more lighter nuclei. So when we break down a heavy nucleus into the lighter nuclei, that is what we call the nuclear fission. In the process, certain mass disappears. Therefore, sum of the masses of final product is found to be slightly less than the sum of masses of the reactant components. Okay, why? Because the process of splitting of heavy nucleus into the lighter nuclei is actually leads to the certain mass disappearance. So that's why the final product mass and the reactant component mass is slightly less than each other. This difference of masses is what we call as the Marx defect or delta. Therefore, as per mass energy relation given by Einstein, energy released in nuclear fission is equals to delta mc square. In 1938, Hahn and Strassman discovered that when 92U-235, that is uranium-235, is bombarded with thermal neutrons, it splits into the 56Ba141 and 36Kr92 with the emission of 3 neutrons along with 200 MeV of energy per fission. The neutrons produced after fission, that is what we call the secondary neutrons. This reaction is represented as 92U-235 plus 0 and 1 equals to 56Ba141 plus 36Kr92 plus 30 and 1 plus Q. Mass defect in this reaction comes out to be 0.2153 AMU. Energy released per fission of 92U-235 equals to 0.2153 into 931 MeV, 200.4 MeV. Thus, about 200 MeV of energy is released in the fission of a single 92U-35 nucleus. This energy appears in the forms of gamma rays, kinetic energy of fission fragments, and the released neutrons. Further, such a huge amount of energy is released in about 10 power minus 9 seconds. It is relevant to mention here that the fission fragments of 92U35 are not always Ba and Kr. Other nuclides have also been obtained, but the energy involved is almost the same in all the cases. The most probable fragment mass numbers occurring in about 7% of the events are centered around As 90 and As 140. The fragment nuclei produced in fission are highly unstable. They are highly radioactive and emit beta particles in succession until each reaches a stable end product. This distribution energy in fission events first appears as the kinetic energy of fragments and neutrons. Eventually, it is transferred to the surrounding matter in the form of heat. About 5 to 6% of energy is associated with neutrons emitted during the beta decay. It is lost to the system. Thereafter, what is a nuclear chain reaction? The fission of 92U35 by thermal neutrons is represented as 92U35 plus 0 and 1 equals to 56Pa141 plus 36K92 plus 30 and 1 plus Q. Now, the 3 secondary neutrons produced in this reaction may bring about the fission of 3 more 92U35 nuclei and produce 9 neutrons, which in turn could bring about the fission of 9 92U35 nuclei and so on. Thus, a continuous reaction called the nuclear chain reaction would start and a huge amount of energy will be released in a short time, therefore in a few microseconds. This reaction is shown in figure. Here, Fp represents the fission product. If we could have a control over this reaction, the energy released could be utilized for peaceful purposes like the energy, nuclear energy production and all. This led to the construction of nuclear reactor or nuclear pile. However, if the reaction couldn't be controlled, the energy release will bring about the disaster effects. That's why I told you that the nuclear energy is actually both the boon and the pain. The boon when you could use it in the controllable manner for the energy requirements, pain when it is uncontrollable, that could have the disaster effects on the humankind and the environment as well. This led to the discovery of an atom bomb. The following points should be considered for a self-propagating chain reaction. First, the leakage of neutrons from the system. Some of the secondary neutrons produced may escape out of the system and will not take part in the further fission. These leakage may be reduced by properly designing the system so that the leakage of neutrons from the system could not be happen. Second is absorption of neutrons by impurities. The secondary neutrons may be absorbed by impurities which are not fissionable. This loss may be reduced by having a fissionable material free from impurities. Third is absorption of neutrons by uranium-238. The natural uranium consists of 3 isotopes with U-233, U-35 and U-238 having the relative abundance of 0.006%, 0.714% and 99.28% respectively. It is found that U-38 is fissionable with fast neutrons, therefore neutrons with energy more than 1 MeV, whereas U-35 is fissionable with slow neutrons, therefore neutrons with energy of the order of 0.025 eV. In natural uranium, as the percentage of U-35 is much less than of U-38, there is more possibility of collision of neutrons with U-238. It is found that the neutrons get slowed on colliding with U-238. As a result of it, further fission of U-38 is not possible. This is why the chain reaction in natural uranium couldn't occur. Fourth point is critical size. In order to have a sustained chain reaction in sample of U-35, it is required that the number of neutrons lost due to the leakage and absorption should much smaller than the number of neutrons produced in a fission process. This is possible if the size of the uranium block is greater than a certain critical value, that is what we call the critical size. The chain reaction once started will remain steady, accelerate or retard depending upon what is called the neutron's reproduction factor or the multiplication factor. This is the ratio of rate of production of neutrons to the rate of loss of neutrons due to the leakage and absorption. It is K equals to rate of production of neutrons by rate of loss of neutrons. If K equals to 1, the chain reaction will be steady or sustained or controllable, you will call it. The size of the fissionable material used is said to be the critical size and its mass the critical mass. This is the stage required for steady power generation. If K is greater than 1, the chain reaction accelerates, resulting in an explosion. The size of the material in this case is supercritical, which leads to the explosion on the site. This is now an atom bomb works. If K is lower than 1, the chain reaction gradually comes to a halt. The size of the material used is said to be subcritical. Thermal neutrons are the low energy neutrons or slow moving neutrons. The energy is equals to or less than 1 by 40 eV. The velocity of thermal neutrons is 2.2 kilometers per second, which corresponds to the velocity of random motion of atoms and molecules in a gas at room temperature. So with this, we have finished this part. It is requested to all of you kindly revise the facts and figures at all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.